Hello, everyone, and welcome to our Twitch session about image computation for microscopy. My name is Markus von Almsick. I'm a consultant and developer for Wolfram Research. And today I'm presenting with my colleague and manager, Shadi Ashnai, who will be responding to your questions while I present. So, what is there in the Wolfram language with respect to image processing in general and image computation for microscopy in particular? Image processing has been a part of Mathematica in the Wolfram language since version 7, and that's roughly a bit more than 10 years. Actually 12 years for that matter. Our goal has been and is to provide the user of the Wolfram language with a comprehensive toolbox for image processing. And that's not just the classical concepts such as filtering, morphology, registration, segmentation in painting, feature detection, and so on, but also the more recent advances that have been achieved in machine learning and neural networks. We do have separate marketing pages for that, and they address in depth the Wolfram language in image processing, machine learning, and neural networks. But that's not today's topic. Here we focus on the so-called vertical application area, that is image computation for microscopy. Other examples for vertical application areas are photography and astronomy. And the idea is here to collect, to showcase that part or that portion of the Wolfram language that applies to microscopy, or rather to the processing of images in microscopy. So let's focus on microscopy. Up front, I'd like to point out that microscopy has grown since its humble beginnings, 400 years ago into a huge field of research. Here, we won't be able to do it any justice. We will, however, be able to cover a tiny portion of the discipline, and we will not cover the vast range of modalities that are there, such as light or X-ray microscopy, transmission electron microscopy, confocal laser scanning microscopy, two-photon excitation, and so on and so on. I think you get the idea. There are just too many modalities. Instead, we rather walk you through some typical application examples to provide you with the idea of how to apply the Wolfram language to your field of interest. And that is, I'm assuming here, is the field of microscopy, life science, material science, forensic, macrophotography, and so on. Okay, so what's the outline of our sketchy walkabout in the field of image computation for microscopy? Essentially, it's this marketing page, and more specifically, it's these appended set of application examples that you'll find here one by one. These marketing examples are basically organized by line. The first line, as you can see here, focuses on the import and export of image data that you get from the microscope, which will basically be going to be the first two examples here. And then the next two examples in this line will address the viewing and the presentation of the resulting images. The second line will address the pre-processing that's quite often necessary to do any feasible work with the data that you obtain. So pre-processing, data extraction, and possibly reconstruction of the data that you assume here. In this last case, it's a 3D reconstruction. The first case, it's the automatic brightness equalization of skewed illumination. In the second case, it's what's called color deconvolution, basically the extraction of the dye concentration given the color in the image, or the composing of images, small images, into one gigantic image via stitching. All right, so these are usually the tasks that you do prior to do before analyzing the image, essentially. Now, that's what we start to do here in the third line. The third line is devoted to the idea of segmentation. Now, segmentation is the technical term in image processing for trying to basically distinguish between foreground or background, or basically to find the area of a certain object in the image. Now, here we have examples that are slightly different in approach. Here we have a segmentation and classification example that goes the classical way. Here we have a segmentation example that tries to figure out how much of the fluorescent dye has been taken up by images in this, by cells in this image. Here we have a 3D examples, because you can also have 3D reconstructions of 3D data sets in microscopy. And last but not least, the example here at the very end, in a way, embodies the most recent advances in neural networks. It's basically a neural network that learns just looking at sample data on how to segment without you basically having to construct a feature set like in the first example that helps you to do that task. All right, then eventually image processing, or for that matter, microscopy, is not just in the business of creating nice images, but at the end of the day, you quite often want to measure something that's been given in your array of data points, or essentially in the pixel values. Now, there are several ways to do that, simple and straightforward ways to do that interactively, that you have tools that you can interactively change and actually measure, let's say, areas, radii, length of strings in the image to quantify whatever you're looking for. Then you can automate that. This is a more automated example where somebody has asked us to come up with an algorithm to measure automatically the thickness of fibers in an image. Here we measure the motion of a whole sequence of images. So essentially a video in microscopy where we quantify the motion of hard tissue as it beats, and trying to figure out exactly where tissue contracts, where it expands, what the motion field is, and last but not least, the pulse, to measure the pulse. Now, life science is not everything in microscopy. There are also application areas in material science and fabrication of computer chips and so forth. So quite often in quality assurance, you also want to measure the differences between a perfect set and a real image. And this would be an example that shows how to measure and detect deviations. Then last but not least, machine learning, or especially when you do screening, it is quite helpful to be able to classify what you see. So in a way to recognize. We have here in the last row several examples that address that issue. The first one would be to classify how many yeast cells clinch together by looking at morphological properties. Here, again, we readdress the example from up here, where we look at blood cells, like in histology, and basically where machine learning algorithm, the support vector machine algorithm, learns how to distinguish two sets of cells just by a set of features in the feature space. Now, that has been machine learning up to 7-8 years ago. Now, more recently, you would try to tackle that with neural networks. And here we have an example where we apply neural networks in different ways. First, we apply to obtain automatically a feature vector or feature space of pollen samples that we'd like to classify. And then on top of it, we use a neural network that does that classification by itself. And last but not least, I think the most challenging example here in this suite of examples is the detection of mitosis using neural cells, essentially detecting in a cell tissue all the cells that undergo mitosis, which is a rather difficult and not straightforward task. All right, so well, this is roughly the walkabout, what I will try to engage now in the next, well, we'll see how long it takes, 10, 30, or even more minutes. You can, if you visit that website here, click on these samples, and this will bring you automatically to an HTML page that nicely outlines what you do. You can copy the commands and so forth. But in order to have a more interactive experience, I'll now switch over to Mathematica, the Wolfram language itself, and display these examples not in the web browser, but in the front end of Mathematica, in particular here in the notebook. All right, so I'm back to the example where we address the issue of importing and exporting data from the realm of microscopy into Mathematica. Well, first of all, I'd like to point out that Mathematica is very well capable of importing a vast range of different file types, image types into the program, into the language. However, as it is, every niche has its own dialects, and that's the same as for microscopy. There are lots of dialects of TIFF or even completely new formats that have been developed and are in use in the microscopy area. So what we did in order to be always up to date, we basically incorporated to a certain degree bioformats, which is a community-driven software tool to read over 140 files into metadata. So what you have to do essentially is load a package. It's called bioformats link, and it's freely available from our site. You do that via this command. Well, we do quickly set the directories, and then in this particular case, I just can, for example, here import a file that is given in the nifty test file format, and I'll do that even calling it from the internet via an HTTP URL address. So this is what it does. It calls up the URL, then imports the URL as a bioformat, automatically recognizes what kind of file format I have, and then I can utilize that file format and display it. In this case, it's a 3D file format of a skull with R for right and L for left. Should have called Dexter and Sinister in Latin. And you can use it in Mathematica. It's readily available. In this particular case, it's not an image, but a 3D volume. You can move it around. You can scroll into it. You can even clip it if you like. So if I were to clip now the top layer down, you can investigate the volume readily in Mathematica without having to do anything up front. So much for viewing it without having to program one line of code. Now, another example of import-export would be this particular example of a mouse kidney tissue that has been provided by Jean-Yves Tinevet from the Pasteur Institute in Paris. This, again, we have to load via bioformat link. So here's a file path. It's an LIF format. And I can just incorporate all the layers of that volume. Essentially, it's not just a single image, but it's a whole stack of images. And we can, for example, use manipulate and go through all the image slices of that kidney in the Z direction and change that as we go up and down. So that's what I have here. You can see there are different dyes, and as we go up and down, we can exhibit different layers of that tissue. So that's just how to quickly view and, well, import and view the data. But furthermore, quite often you need extra information. So if I were to read in the extra meta information, I would simply have to specify that as an argument here, and this would automatically give me then the size of the image and so forth as I go through here. But furthermore, there are quite often extra meta information, in this case OME meta information, giving in the format of an XML file. And since this is XML, I can readily use all the pattern matching that is built into Mathematica for XML parsing. And for example, define rules that extract me the pixels that are used in this image. And this will now tell me how many pixels there are in each direction, what the pixel size is going to be, and so forth. Or I can extract from the meta information the voxel size. And the voxel size is, as you can see, even given with the appropriate units in micrometers, 1.5 micrometer in every direction. Well, actually not quite true. In the X and Y direction, the Z direction is slightly smaller, just has a size of roughly 1 micrometer. You can call up other information that may be particular to your modality. In this case, we're looking at a stimulated emission depletion by lasers. So we look at the wavelengths of the lasers, which we can call up here. And you can see the wavelength involved in this measurement is 405 nanometers up to 633 nanometers. So just that gives you an idea that essentially there's all the information available to you if you have to incorporate or read in information about microscopy data in files. Now, given a quick remark, you can also attach microscopes via USB. When you want to have direct interaction with the hardware, then that very much depends on the API that the provider of the hardware allows you to contact, and that of course also is available in Mathematica, but that would imply dedicated programming to hook up to the API that the hardware provides. So this was now a simple way of just importing images. Give me, or believe me for that matter, that you can readily export these images as well. Now, assume once you have data already loaded via import. In this case, it's a rather big file. It's 1900 times 1400 pixels. And that's when it starts to get a little bit clumsy in the Mathematica, because your screen may not have enough pixels, and that way the notebook may not have enough width to essentially display the image in full resolution. And for that purpose, we have a dynamic image command that allows you to dynamically move in or out, or pan or zoom into your data. So I could, for example, just take here the sidebar, make it smaller, thereby zooming into the image. I can move around. I can use zoom in and out buttons. I can pan, as you can see here. I can hold the Option key and, the Shift key, and zoom in and out. So this is a great way of investigating your image data within Mathematica. I haven't done it here, but you can also link not just one, but two or several of these essentially viewing panes, and thereby synchronously view or investigate not just one, but two data sets if they are related to each other. All right, so much for viewing your images in Mathematica. Now we want to dress the data up a little bit. And let's assume you have a very nice image. This is an image of a little chalk grains. And they have been obtained via an electron microscope. So since electron microscopy only renders black and white images, you're doomed to just get these rather sober-looking grayscale images. And if you were to dress it up and make an impression, but with false coloring, you can of course do that painstakingly yourself, or you can utilize now one of those many aspects or features that we have in Mathematica. Basically, go into another application area like neural networks and obtain tools from that particular area and apply to microscopy. Now, in this particular case, I'm referring to a neural net that we have in our neural net repository. It's a large collection of neural nets that have been established over the last few years with pretty good properties. And this is a neural network that essentially can take grayscaled images and colorize them. Now, this has been trained on natural images, not on microscopy images, so it may not be the kind of coloring that you would typically get in microscopy, true coloring. Well, if you can even talk about true coloring at that magnification level. But if we can use this model, just load it in here, and this loading of model will give us a neural network of rather considerable size with lots of convolutional layers. I'm not going into detail here. And this neural network this neural network we can incorporate into a built-in command. First of all, I call the command here add_color, and what it does, it basically takes the image, runs it through the net. The net returns an array, which essentially is a color version of that image that is being converted back to an image. And that image is then resized to the dimensions of the incoming image. And then we combine the color information that has been obtained via the net and combine it with the image, the input image itself, in an LAB color space. So that's what this little command does. And let's see how it works. We just plug in the image, the grayscale image, and get a color image out. And you may say, well, this is already fairly reasonable aesthetic coloring. We can also change that by basically rotating the color axis in the LAB space and thereby getting different hues for that particular image. Or you can utilize this by segmenting certain parts of an image. In this particular case, we're looking at the eye of a leafcutter ant. So this is the eye, and we may want to give it a different coloring than the background. So this would be the default coloring by the network that we just obtained. But I can just take a mask and rotate part of the image in color so that I get a more greenish background around the eye. And then I take the original color of the eye and paste it in there, and thereby I get a coloring that emphasizes the particular feature that I'm interested here. So this is a more kind of a less scientific but more artistic way to apply Mathematica to microscopy images. So this concludes my little tour through the first line of this table of contents, where we addressed importing image data and presenting image data. Now, before we can analyze essentially image data, sometimes it's quite, or well, it's not sometimes, but quite often it's necessary to pre-process the data. And this is a very, well, typical case that if you have not one of those really good microscopes can happen to you very easily, and that is that the illumination of your sample isn't the way it's supposed to be. In this case, what you see here, actually, I don't know what we're looking at here. I have to give away on that one. But what you can see clearly here is that we have a darker area on the right-hand side and it's brighter on the left. So if we were to do some segmentations and so forth, or quantifications, we may get actually good data on this part, but bad data on the right-hand side. So almost mandatory first step is to do what's called brightness equalization. And this is usually done by the following procedure. What you do is you take an image of your microscope, but without a sample inside, essentially. So a blank image, or what's called a flat, a flat field, or flat field image. And that flat field image will not have any object in it, but it will reflect the illumination or the illumination property of the area you're looking at. And if there's any unevenness, that flat field will tackle or basically grasp that. And then you can just later on take an image, divide it by a flat field, and that division will then even out any unequal illumination. Now, quite often, though, you have the problem, you have an image like this, and you have never, or your colleague has never taken a flat field image. So what you can do would be the following. You first basically try to obtain the background in the image where you assume that that you find the standard distribution of brightness. And then what you can do is run this through the command brightness equalize, which essentially will try, in this white area, try to fit a polynomial distribution to the brightness it can see there. And that is then the model of brightness that's being applied as a flat field distribution to the image. And that will allow you to obtain a much better image at the end. So this is now an image where you can see that the dark side has been removed. Or if I were to compare directly via flip view, I can now toggle forth and back, and you can see very nicely that the quality of the image is now far more homogeneous. All right, so that would be an example of a pre-processing step that you may have to encounter or may encounter in microscopy. Another step would be to basically extract from the light data, so from the color essentially that you see, some other property that's in your sample. In this particular case, we have a tissue that has been dyed with two stains. In the first case, it's hematoxylene, C19, and DAB standing for diaminobenzidine. The tissue, depending what type of tissue it is, will take up different concentrations of these stains. And depending on how much stain there is, you get a darker color or more full color of blue or green, I think, in this particular case. Yes, hematoxylene has this color, it's greenish. Diaminobenzidine is more bluish. So I can just take the image in, and then once I know the color for my microscope, well, no, I should phrase it differently. Once I know how the CCD, essentially the camera, how the camera picks up the color of my dye, because all cameras have slightly different color sensitivity, then I can specify that color sensitivity in as an RGB vector, just like here in Mathematica. And this RGB vector will tell me essentially how much dye there is if I measure a certain color. So what I can construct first is a kind of a matrix that takes the dye concentration and converts it to RGB, because that's usually what I can measure or what I can read from the literature. So that's essentially what I have here, a color mixing matrix. Now, in order to do the reverse, because I have the color here, but I'd like to know the concentration, I get the pseudo inverse of this matrix. So that's, in a way, my color demixing matrix. And in order to make this work well, I have to apply now this color demixing matrix to my color space here. However, one last little trick, I have to do that in a log scale for the intensities, because if I have a dye, and the more dye I have, it will basically exponentially increase or decrease the color coming through the more dye I have. If I basically have twice the amount of dye, it will keep exponentially block more and more of the light coming through the microscope. So in order to compensate for the exponential property of absorption of the dye, I have to basically work in the log, apply the logarithm to the intensity, color intensity. Then I apply the demixing, and then I essentially convert it back and display the result. So the command separate stains takes the image. When I know the demixing matrix, it will come out with an image that basically displays the concentration of the first dye, and here in the second image of the second dye. And once I have these concentrations, I can, of course, make measurements on the dye uptake, or if I want to, I can then reconstruct the images slightly differently. I can here, for example, specify the dye and the color, or I can have a false coloring, like in this particular case, that I take red instead of blue, or vice versa here, blue instead of the yellow color. All right, so that is an example of converting color or images into measurements that depict here, in this case, the concentration of stain uptake. Another issue that you may have when you do microscopy is that usually your field of vision is very small, because you enlarge quite a bit what you see of what you see. Therefore, you don't see much. You don't see very much to the left or right. The area that you essentially see when you magnify tremendously tends to be small. But quite often the samples that you want to investigate aren't small at all. So quite often what you do is you have a microscope, and you have to move the stage on which the sample is mounted, and take image after image after image, and obtain eventually an array of images, and then stitch these images together. And we'll just do one example of stitching here in Mathematica. It's being done. Let's assume we have these two beautiful microscopy images that I like to combine. Now, one nice thing, in contrast to other images in the real world, these microscopy images usually only differ by translation, because the stage usually doesn't rotate, it doesn't move up or down, so you don't get closer or further away from the sample. But all you do is you translate an X and Y perpendicular to your optical axis of the microscope. And that's the only motion that you have to compensate or try to determine when you stitch two images together. Now, there's a command in Mathematica, it's called image align. Image align can do, as it says, the alignment of two or more images, and it can do that in many different ways. What's completely sufficient here for our purpose in microscopy is the following. The only transformation that we have to take into account is, well, transformation class are translations. We don't have to consider scaling. We don't have to consider rotation. We don't have to consider perspective transformations. And if that's so, especially if translation, a very good method for alignment is the so-called Fourier method. very quickly, the idea is you do a Fourier transformation of the image, and then a translation essentially is locally nothing else but a complex phase transformation. And when you basically compare now pixel of one image with the pixels of the other image and just look at the phase difference that you may measure all over, that phase difference in X and phase difference in Y essentially will tell you what the overall translation has to be in order to align those two images. So let's do that right here. Well, here we just get the border dimensions because that's easier to use down here. But if I were to use or to obtain the transformation here, I'll see that I would have to move the image in X direction 271 pixels and in Y direction minus 17 pixels, the second image that is, in order to make it overlap perfectly. And we can quickly do that. And you see here, this is a perfect alignment of those two images. And of course, this can be iterated. This can be applied to an entire array of images. And thereby, you can create large images, even though your microscope one at a time may only generate fairly small images. Typically, in the industry, you have 1,000 times 1,000 pixels that you can then attach to larger images. All right, let's get even more fancy. Let's assume we try to get a 3D model of a sample under an ordinary light microscope. Now, what I have here, this is just an image to depict the thing. What I have here is the actual data set. And the data set is nothing else but essentially a so-called focal stack. A focal stack basically means I have taken the image or the images of the sample with different focal length. So if I were to animate this, then this may look very familiar. It's just like turning the knob on your microscope and trying to get the object of interest into focus. And you'll quite often notice that it doesn't work. The field of, not the field of view, the, what is it called? The area or the depth, the field of depth, sorry, that's what I was looking for. The area of the depth in which the image is in focus is in contrast to, let's say, regular photography, very, very narrow, very thin in microscopy or macro photography, which is, in this particular case, a burden, but it can also be a virtue. Now, the burden, of course, is that you can't get it into focus everything. So what you can do is construct an image that is in focus over several focal lengths. And that's a command that we have in Mathematica that's called image focus combine. Now, what image focus combine does, it essentially looks at all the layers, just takes from every layer or from every focal plane, just the part of the image that appears to be in focus, combines everything, and thereby I get an image that appears to be in focus everywhere. Now, we can quickly, actually, okay, that's a built-in command, but we can even quickly rebuild this command ourselves by just quickly explaining what we do here. I apply a so-called Laplacian Gaussian filter, a filter that just basically measures local changes, and use that as a criterion to figure out if something is in focus or not. So essentially, from a Fourier spectrum point of view, you're just looking at the very high frequencies, spatial frequencies in an image, because if things are blurred, these are the first features that are depleted, that are gone. If everything changes slowly, then if you blur, that doesn't affect it. But minute changes, or very local changes, they get blurred and washed out very quickly if they are not in focus. So by looking essentially at a Laplacian, at the output of a Laplacian Gaussian filter, I'm looking at those parts in an image that are, well, that exhibit high spatial frequency features and thereby appear to be in focus. And you can see that the part that is in focus goes from the center to the outside and back again. Now, this appears thereby to be a good feature detector to see if something is in focus or not. And then all I do here is basically stack all these things up. I just always do what's called a non-max channel suppression. That is, I now suppress all the image parts that are not maximal with respect to this feature, and then add all these things together, and thereby I get the image that I had that's all in focus. But essentially what I have here now is essentially a stack that tells me where things are in focus. And this information I can use as a depth clue. A clue that tells me where or how far that object is away from the lens. And this is what basically I just did. This stack of responses I basically now convert into a depth map, and this is the result of the depth map. And what I see is that, well, it is not very regular. It seems to be quite a few features that seem to be close, far away, and so forth. And the reason for that is that the depth estimation very much depends on the presence of sharp edges. So if I now basically create a kind of a confidence map that tells me where I can be confident about my depth estimate and where I can't, I can create a depth map with the confidence and then fill in all the parts in the depth map where I'm not confident about the depth. And that way I obtain a much more regularized depth map. And once I have that, I can project the image data on top of it. And this then gives me a 3D image of the object. In this case, it's a pollen that was under my microscope without actually having a 3D microscope. This is just basically going via the estimate of the focal length. So kind of a poor man version of a 3D microscope just by looking at the focal length of every image that you have in the focal stack. All right, so much for that. Let's move on. And on means going to the next line, which addresses segmentation. Now, segmentation is the art of actually recognizing areas or objects in an image to a certain degree, maybe not classifying them, but basically telling apart what pixel belongs to a certain object and what doesn't. It's a tricky thing. And 10 years ago, people at image processing conferences basically would have told you, well, image processing are two things. It's registration, that basically means stitching. And the other part, at least biomedical imaging, is segmentation. Now here we do our first segmentation. We'll have more coming down the line. The way to do it is a very simple way of segmentation, and that is we just binarize. Now, binarize works fairly well because the background is always brighter than the foreground. So if we color negate that, we'll have a pretty good mask here, binary mask that tells me where there is a cell and where there isn't a cell. And what we're looking here basically are blood cells, red blood cells, and there are normal blood cells, they tend to be round, and the so-called Burr cells, abnormal cells that basically have all these little spikes. And now we just try to achieve the following task. We try to tell apart how many healthy or normal blood cells there are compared to those so-called Burr cells. And this would be a typical way to go about this in Mathematica. First, I do what's called a distance transform. Essentially, I look how much each pixel within a cell is away from its boundary. And that basically gives me kind of a small mountain for every cell. And the peak of every mountain basically tells me where there is a center of a cell. So I can get these center markers for every cell. This has the benefit that this still works fairly well if you have even overlapping cells. So it's kind of a more robust way to go about this. Another segmentation tool that we have then in Mathematica is a so-called watershed method. The watershed method basically assumes that the image is like a landscape, and areas where water flows together tend to belong together. So if there's a kind of a common sink, then that area is a segment, and that works pretty well for the dark basically for the inverse of this image. And this gives me then a nice segmentation of all the cells that are in the image. And now that I have all these segments, I can do what's called here Hothead, a morphological transformation. I'm not going into the detail here. That basically cuts away all the features that are of scale 8 pixels or smaller. Now, what it does basically, on a round cell, it doesn't cut away anything because everything is smooth. But for those Burr cells, it cuts away these spikes. And the more spikes I have, the more I can rest assured that I'm looking at a Burr cell in contrast to a healthy cell here. So this looks more like a Burr cell. This looks like a healthy cell. And just by essentially measuring the difference between a segment with and without spikes, I can run this through a component selector in Mathematica, going for area versus the mean. And just by basically then getting the right threshold, you can, in a very the classical approach in a way, distinguish between Burr cells and normal cells. So what we have done here is we have segmented the image. Based on the segmentation, we have extracted certain features, like how many spikes I have and how large the cell is, essentially. And then last but not least, we have found a threshold that distinguishes between the group of Burr cells and the healthy cells. Now, that is a very classical, down-to-earth approach, and we'll show much more elegant ways to do this in examples to come. Another application example, which I just fly through quickly, is a very typical one, which you may encounter in fluorescent microscopy. The idea is essentially that you have a fluorescent marker that you expose the tissue to, and then you want to figure out exactly how much of the fluorescent marker has been taken up by a cell. Now, this is a typical image that you may get. So the image down here, it has essentially two color channels, one for every fluorescent marker. The blue marker just signals the cells that there are, and then special cells. I'm sorry, forgive me for not knowing exactly right now what properties these stained red cells or brain cells of reds have. They are then of a different type, have different properties, different receptors, and quite often you have to quantify how many of the cells that you are looking at here do have this different receptor, have taken up the other fluorescent as well. So as we have to go through this, we can first extract the stain with the cells. Here's the image with the fluorescent that has been taken up, the second one. Then we can apply like for bilateral filters to get a more regularized, less noisy image. Then just extract the background because that's not going to be part of our calculation. And then essentially what we have here is we have applied a Laplacian Gaussian filter to always roughly estimate the center of each of these cells. So at the end of the day, just by applying the Laplacian Gaussian filter of a given scale and doing a min detect, we found all the positions of every cell. So once we have that, we again do a watershed component algorithm of segmentation around each of these dots, and each dot then gives me one cell that I would have to then investigate. And then investigate it as follows by saying, okay, for every cell here, I'd like to figure out how much fluorescent is superimposed on that particular cell. And then I get essentially here a histogram distribution that I know I have here, let's say, to 170 cells that just have very little uptake. And here I have many more cells that have a more substantial uptake of that fluorescent. And last but not least, I can even manipulate that. I can see what cells have taken up the fluorescent up to a certain degree, which is here given by sigma. The higher I push this, the fewer cells actually qualify. And the further I lower that threshold, the more cells qualify as having uptaken that fluorescent. And of course, then I can readily count the cells or even generate a distribution without having to do this rather tedious task myself by counting cells that have that fluorescent marker. Of course, segmentation also works in 3D. Here's an example of a tissue taken from the hippocampus via electron microscopy. It has a 10 nanometer resolution, and as far as I can tell, I think we got that essentially from the Blue Brain project from the EPFL in Lausanne. Here we just basically like to demonstrate how we can take this tissue, where we just basically now walk through from top to bottom, and basically extract a volume here, or basically these are neural cells, basically a cell body. Now we do that in a straightforward manner. We take the slices, and then of a particular slice, I just basically mark here a location in a cell. For example, this part of an axon, I mark as a seed. And once I have now the information of that seed, that by the way I obtain by clicking, by getting the coordinate like this here, I can read out the coordinates, I can put them here, and then I can do region binarize. Now, region binarize is a segmentation technique that is very helpful if you know that you have a connected region to a segment. It basically starts to collect all the, in this case, voxels that are not more than different by 0.2 of the grayscale value here. And I'll run this segmentation, and you see this is giving me now the cell body. And just to visualize that this is a reasonable segmentation, I superimpose that on the layer of that volume as I move it up or down in Mathematica to see that actually I did correctly segment that particular cell body. So all these tedious cell segmentations are possible. And last but not least, to conclude this line number 3 about segmentation, I quickly like to point out that we also have neural networks that can be trained to do segmentations on specific tasks. Now, this is a neural network, a so-called neural network that I will describe, that has been trained to segment these types of cells. These are rather nasty cells. They are glioblastoma cells, so basically cancer cells in your brain that you really don't want to have there. You will see to what precision this neural network can go to basically precisely segment these rather, well, irregularly shaped cells. So you can't really, well, long story short, it can segment these cells very well. So the network itself, again, comes from our network repository. The set cell or network structure is as follows. It essentially takes the input image and has a local neural network, convolutional network, that helps it to essentially extract features. And then part of the segmentation based on low features or on these very rough features is then transmitted across onto the other side of the U network, basically where the image or the segmentation mask essentially is assembled. So you do that for low-level features at high resolution. You do it for higher features at lower resolution. As you go down and up again, that's why it's called a U-based or so-called U network. And these kind of U networks, they can be trained on all kinds of data to obtain this kind of segmentation capability. Now, this particular one had been trained on this set of image data. And what I have here is a Mathematica command that is built on this network. So the network is applied somewhere here. Let me quickly find it. Here we go. Essentially, it's rewritten as NuNet. NuNet is applied to the image. And we do this in the following way. This network has been trained to work on a specific image size. The image size has to be 572 times 572. Now, if I have an image with a different size, I basically have to partition it, and all the partitions with padding have to go through this network and then have to be reassembled. And that's all the bookkeeping that's being done here. It's a little nasty to follow up, so I'm not going to detail. So once I have this defined, I can actually apply it to the image. This will then generate a mask basically in this particular case of just zeros and ones. And then I can use that mask, convert it to an image, and apply it to the result. And just to show that I'm not making this up, I generate it again. It will automatically classify precisely or segment precisely where these cells are. So this can be then done for any kind of nasty cells that you have. If you have enough image data, you can train it that way. All right. Right, so let's speed up a little bit. I'm seeing I'm using up too much time eventually. Now, once we have segmented things, we can actually go one step further and we can measure things. Now, if it's very simple and you don't want to go through any length of programming, sometimes it's nice to just being able to do it interactively. And we have commands that allow interactive programming or interactive editing of images. So what we have here is a dynamic image that you have seen already, which allows you to zoom in, pan in, or pan around an image and so on. And we can put all of this in a manipulate that allows you to change objects that you may have in front of the image. Like in this particular case, we essentially have a circle with a radius r and a center point that we can change. So I run this on that image. And what you see here is what I get is this kind of circle. Now I can use that circle, change the radius, and essentially automatically measure the area under that circle. So if you were to quickly measure, for example, these structures in testis cells of frogs, I think, you can quickly come up here with 40,000 micrometers squared without having to go through any kind of elaborate automatic schemes. Now, however, quite often, if you have to work through many of these examples, it's quite nice to have an elaborate scheme or automatic scheme to do the job automatically. And for that purpose, I'd like to show you this example. This example was given to us on an M&M conference way back. I don't know which one it was right now, by eSpin. And they were looking essentially for an algorithm that would automatically measure the fiber thickness under a microscope. So they were just looking at tissue, a cloth essentially, and the question was, how thick are these fibers? So essentially what you can do in Mathematica is very quickly develop your own little routine to do certain tasks that nobody has done before. So in this particular case, I just came up with a quick essentially edge detector based on a Galois filter that can be oriented. So it has an orientation parameter phi, and phi can be changed so that I can detect now, let's say, horizontal edges, vertical edges coming from the left, vertical edges come from the right, and so forth. And if you, well, make it a bit more extravagant, you can go ahead and say, well, I take this filter and then also shift perpendicular to that edge. And that would allow me then to, again, do edge detection, but let's say I do now horizontal detection, and then I move R, then I can move that edge by a certain shift inward or outward of that fiber, depending how you see it. So if I move that in the fiber inward, then I can combine this and do the following. I can create an R stack. The R stack, well, I just called it R stack, has the following property. I have applied this shifted fiber edge detector or filter twice and multiplied. I basically detected the left edge or one side of the edge of the fiber, moved it inward, and detected the opposite side and moved it inward as well. Now, if I move both of these detections sufficient that they basically meet each other in the center of the fiber, they will light up. If they don't meet, they stay dark because one side will be zero essentially, and that doesn't amount to anything. So by animating this, you see what I got, going through all the different orientations. For every orientation and for different R, oh no, sorry, actually I did already add here some overall orientations, but for the different radii estimates, I get here layers that basically light up for a certain radius. And that basically means that at this position, the fiber actually had that particular radius. But essentially I have to probe for all reasonable radii available. So that's what I've done here. And then by essentially extracting the correct R and the center fiber, I can first of all denote all the measurements I have done in this particular image, and I can extract at the end of the day the histogram of radii of all these fibers, and you can see that essentially it looks like you have two different fibers in this particular set. One's that around, well, have a typical radius of 18.25 or so, and another set of fibers that cluster around a radius of 2021. Okay, another example now away from material science, further back to life science. Here I'm looking at a little motion picture, a sequence, a video that I import now and that I animate by going through list animate in Mathematica. And what I see here is tissue under the microscope, and this is hard tissue as it beats. So we can see these, well, in some cases, somewhat minute and irregular movements. But what I'd like to do here is to quantify that motion and see where things contract, where they expand, and so forth. Assuming, of course, that there's no true motion perpendicular to the image plane here. All right, you can just for the import, first of all, some metadata telling me that here I'm recording at 60 frames per second. then I can take, just for the to speed up the processing a little bit, take a small excerpt from the video, some 64 frames that essentially make up roughly one beat. And then I run this through image displacements. Now, image displacements is a command in Mathematica that essentially does what's called optic flow. It looks at subsequent images and sees how patches in these images, how they move, how they translate. And from that, it constructs a vector field that basically encodes the motion from of all the image patches in this video. Now, usually you have noise associated with it. So what I do here is I regularize the whole motion picture or the whole field by running it through a Gaussian filter. And then I essentially can superimpose a vector field on the video. Now, I've done that prior to this talk because this takes roughly 2 minutes, which would be rather boring. And now what you see here is that very same video, but now with a vector flow field imposed. And you can see roughly how the motion goes down and up again, and how this motion field is constructed. Now, you may want to go one step further. You may want to, what do I do here? Calculate the amount of motion. That basically you take all the image displacements, you calculate the norm of all the vectors, you add all the vectors up, and then you get what I call here a signal in time that just basically denotes the motion. And then I can find the peaks, and you can plot this, and this basically tells you the hard motion. And then with every peak, this can be then counted as a beat. And when you take the difference of all these beats, you can basically deduce that you have here a heart rate of 109 beats per second. And last but not least, just to show that we can also calculate the divergence of the vector field. The divergence essentially tells you if an area, from an area in the field, everything flows away or if it flows into an area. And that tells you if a part of the tissue is contracting or not. And this is now what I've done in this animation. The red part is contracting, the blue part is doing the opposite, and this gives you then an idea how these cells essentially make up as beating heart. All right. Very quickly, if you have, let's say, images from material science or in a production of, in this particular case, of integrated circuitry, you quite often have, let's say, a mask where you know everything is correct, or you know you have a chip that is perfect, and then you can compare the perfect chip to any other chip that goes through your process, and thereby make sure that there are no deviations. Now, what I've done here is I've taken one circuitry from the internet and basically compared two very similar parts of that circuitry, which are actually not the very same. But in order to make this comparison really work well, I do the following. I do split up the entire image here into small image parts. I align every part of the image one by one, remove alpha, look at the difference, crop overlaps that I have created here in the partition, and then assemble everything back together. And this way I get a very nice difference image that tells me where the image actually differs, not just because of slight misalignments, but because of the content of the image. And then I can highlight that, and then that tells me exactly where in the circuitry I have differences or not. So that would be a typical thing that you may want to program if you have quality assurance objects or issues. All right, given time, let me skip this particular one. This is now the last line in the example of the market page that deals with classification and detection. So here we classify cells, as a matter of fact, yeast cells, and depending on the fact if they clutter to clusters or not, I would like to tell that apart. And this is done now, well, just to go through that quickly in the following way. Essentially, I do a segmentation up front. Once I have a segmentation, I can always calculate the perimeter of a segment like this one here or this one here. And once I have that perimeter, I can compare that to a convex perimeter. So basically one where the edge only moves, turns inward and never outward. So something of that sort. That's a convex contour around an object. And then whenever the difference between that contour, that convex contour, and the actual contour starts to deviate, like here, I can tell that I have here two lobes of cells basically clustering together. So this is a clear indicator that I actually look at two cells that got stuck together whenever I count these points. And this can then be generalized. And at the end of the day, you may come up with all these cases that you have pairs of yeast cells just by counting two of these non-convex lobes. Here you have a simple one, again, a pair, or you may have a very complex construct by looking at a spectrum of convex to actual edge distances as you move around that cell. And that can then help you to quantify how many yeast cells got stuck together, for example, and how many didn't. Another example you classify is, again, back the example that I had a few minutes ago, the one about red blood cells, where you have to distinguish between normal blood cells and Burr cells. Now, this is, again, the image. It was masked. But now we do not classify ourselves. Let me just go through these examples. But we have machine learning algorithm classifying these cells automatically. And that's done the following way. You first have to obtain a few samples. You can do that by, for example, clicking on this image and say, here are the positions, bang, 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 and so forth, where I have normal cells. Then you can copy those out and give here the positions, read out these cells. And I can do the same for the Burr cells, just to get a few examples. And then I have to create, again, a feature space. That's essentially the same feature space that I had before, with morphologically taking away the spikes and then calculating the difference between the rounded version of the cell and the spiky ones. And then I sent all of this through, where is it? A classify command in Mathematica. So that's a built-in automatic machine learning command, in this case, applying support vector machine, that takes a training case and tries to come up with a good way to partition now these two groups of cells based on their features that I've just extracted. And if everything works well, this will give me a plot that will show the probability distribution that this classifier function now attributes to every point in the feature space in order to group it into a Burr cell or a normal cell. And here you have the area now, bluish, where they go into, well, I guess Burr cells. And here's the area where you are looking at normal cells, where here essentially you have an area where you can't really tell them apart. And I can depict now this feature space with the different cells and see if they actually confer to what I had. Yeah, that looks pretty much like a reasonable detection of Burr cells. And so essentially, just to get back up here to this, it automatically creates the area where you assume to have Burr cells in the feature space and the area where you don't. So that's the classical way of doing classification. And now, last but not least, I'll come to the very last example because I'm running out of time, I have to admit. I'm looking at the most recent way to do these things, and that is via neural network. So I can even look at a much more challenging example. The example is looking at different pollens under the microscope. Basically, I took 6 different samples from my garden, tulips, hibiscus, and so forth. And the data basically looks like this. This is a flower, and here are just a small number of samples, so just half a dozen And now the problem, especially when it comes to neural networks, is that you usually have to have a large number of training examples in order to train a network reliably. Now, this obviously is not the case here, so I have to do a trick, which is a little bit like what a human being does as well. Let's say you are a radiologist. When you classify your images that you're looking at, you actually base your knowledge of seeing on what you learned as a toddler. So basically, part of what you learned about actually seeing things has never been applied to your task you're looking at right now, but was learned in general. And this is exactly what I do now. I basically run this set of augmented samples by just generating more samples, flipping them through what's called here a feature extractor. Now, this feature extractor is a neural network, or are neural networks that are trained to come up with features for certain data types. Now we have, for example, here a neural network that generates a feature vector for images. And this is exactly what we use now for the small amount of data that we have augmented, though. That means generate more data by reflecting, mirroring, rotating the images. This essentially will create a feature function that takes any object here, any set, and converts it into a vector. Now, this will take a while. That's why I will stop this calculation. And what you essentially get is then for every image, you get a feature vector. And this feature vector then I can use to first visualize in feature space. However, this is now a feature space of 157 dimensions. So I use a stochastic nearest neighbor extractor TSNE embedding to reduce that to 3D. And just looking even at this 3D space, which for some reason here I can rotate, I can see that the different pollen types do get grouped fairly well. Now, this grouping already indicates that there should be a classifier capable of segmenting these groups and thereby classifying them. And that's exactly what I do here. Well, actually, let me stop this. I did not fully evaluate this. So what I get once I train this is a neural net just of 2 layers that basically comes after having extracted with another neural net the features. So this is just a classification part of a neural network. And when I apply this trained network on just these few samples, 2 samples that it hasn't seen yet, it will do an okay job by correctly classifying all these different pollens into these 6 different classes. All right. Without much ado, you can get bigger networks that you can run on more data. And for example, you have 1800 data steps to train and test. And then if you run the network on data that you haven't seen and you train it, then at the end of the day, you get, in this particular case, trying to figure out where there's mitosis in tissue, confusion matrices like this. That means it has to indicate if there's a mitosis going on or not. If there's mitosis, has guessed correctly, not guessed, but predicted correctly in 87 cases that there is mitosis. If there is actually mitosis, it has gone wrong one way or the other in 18 cases and 20 cases. And then when there was no mitosis in the cell, it has predicted in 427 cases that there isn't. So this is a typical scenario where you have neural networks and we have to try to predict a rather tedious and difficult task in image processing based on lots of data, and where you have, in this particular case, achieved an accuracy of 93%, which may not look great, but considering the fact that human beings usually also have an error rate of 10%, doesn't look too bad at all. All right, so sorry that it has been a rather fast introduction now at the end through all these pretty fancy and rather modern ways of digesting images, particularly now microscopy images. Let me quickly, before I conclude this Twitch session, make a few remarks. Of course, I only scratched in a way the tip of the iceberg. A, there is more to microscopy, and B, there's more to Mathematica than I could show now in this 1 hour Twitch talk. But there's more to look at on the internet. For example, there's a blog post about computational microscopy that we have. Just go under the blog post on wolfram.com and you'll find it. Or there have been people working Mathematica a long time ago already that have written books that relate to microscopy, not just digesting the images of microscopy, but in some cases building microscopes, electron microscopes, or tunneling microscopes in this particular case, that are out there. So feel free to roam around and see what we have to offer. Okay, I'd like to stop here. Sorry for going a little over time. If there are any questions, I stop sharing now. Maybe at this point, my colleague Shadi may want to take over if there have been any questions that have been outstanding or of general interest. Okay, I just get the remark or the note via the chat that there are no questions, in which case I'd like to thank you for your time, and thanks for looking into this Twitch session, and I hope it has been helpful answering questions and has been productive in giving you a good idea of what can be done in Mathematica with relation to microscopy images. Thank you.